Welcome to Lecture 5 of the GMP and Quality Fundamentals series. In Lecture 4, we explored risk management and OOS investigations, where quality decisions get real and pressure is high. In this lecture, we dive deeper into deviation management, out-of-trend results, and root cause analysis techniques. Deviations are inevitable in any manufacturing or laboratory environment. What separates good quality systems from great ones is how deviations are handled. Today, we will learn what deviations are, how to classify them, the difference between OOS and OOT, and advanced techniques for finding root causes. A deviation is any departure from an approved instruction, procedure, specification, or standard. In simple words, a deviation is when something does not go according to plan. Examples of deviations include temperature during storage goes above the specified range, a step in an SOP is missed, equipment breaks down during production, a test result fails specification which is OOS, or documentation is incomplete. Deviations can be big or small, critical or minor. But all deviations must be documented and investigated. Deviations indicate that something unexpected happened. Without proper deviation management, problems repeat, risks increase, product quality suffers, and regulatory findings accumulate. With proper deviation management, problems are identified early, root causes are found and fixed, systems improve continuously, and regulatory compliance is maintained. Deviation management is not about blaming people. It's about improving the system. Deviations can be classified by severity. Critical deviation directly impacts product quality or patient safety and requires immediate action. Examples include contamination, failed sterility tests, or wrong ingredient used. Major deviation has significant impact on quality or compliance and requires thorough investigation. Examples include temperature excursion, missed calibration, or incomplete documentation. Minor deviation has limited impact on quality and lower risk. Examples include late documentation or minor clerical errors. The classification determines the investigation depth and urgency. Let me give you a cake example for deviation classification. Scenario 1: baking temperature was 200 degrees Celsius instead of 180 degrees Celsius. Classification is major deviation because it affects product quality. Action is investigate, assess impact on batch, possibly reject. Scenario 2: baker forgot to initial the temperature log. Classification is minor deviation, it's a documentation error with no product impact. Action is investigate, retrain, correct documentation. Scenario 3: raw eggs were left at room temperature for 6 hours, creating contamination risk. Classification is critical deviation, it's a safety risk. Action is immediate investigation, batch rejection, CAPA implementation. Different severity equals different response. Now let's talk about OOS versus OOT. OOS, which is out of specification, means a test result falls outside the approved specification limit. Example: specification says less than or equal to 1.0 parts per million. Result is 1.3 parts per million. This is a clear failure. OOT, which is out of trend, means the test result is within specification but shows an unusual trend or pattern. Example: specification says less than or equal to 1.0 parts per million. Results over time are 0.2, 0.3, 0.3, 0.8 parts per million. The 0.8 is still within spec, but the trend is increasing. OOS equals failure. OOT equals warning sign. Both require investigation, but OOT gives you a chance to act before failure occurs. OOT detection is proactive quality management. If you only react to OOS, you're already late. The product has failed. If you monitor OOT, you can identify problems before they become failures. For example, Week 1 heavy metal result is 0.2 parts per million. Week 2 is 0.3 parts per million. Week 3 is 0.4 parts per million. Week 4 is 0.7 parts per million. Specification is 1.0 parts per million. All results pass. But the trend is clear, something is changing. Action is investigate now before it reaches 1.0 parts per million and becomes OOS. This is the power of OOT monitoring. OOT can be identified through statistical tools like control charts, trend analysis, and standard deviation calculations. Visual inspection includes plotting data over time, looking for patterns or shifts, and comparing to historical data. OOT triggers include result approaching specification limit, sudden jump in values, consistent upward or downward trend, or unusual variation. Even if results are within spec, if they look unusual, investigate. When a deviation occurs, follow a structured process. Step 1 is detection and reporting. Identify the deviation immediately, report it promptly, don't hide it, and document when and where it occurred. Step 2 is initial assessment. Assess immediate risk, take containment actions if needed, and determine classification as critical, major, or minor. Step 3 is investigation. Gather all relevant data, interview people involved, review procedures and records, and identify what went wrong. Step 4 is root cause analysis. Find the true underlying cause, don't stop at the obvious symptom, and use structured tools like 5 Whys or Fishbone. Step 5 is CAPA implementation. Corrective action fixes the immediate problem. Preventive action prevents recurrence. Set timelines and responsibilities. Step 6 is effectiveness check. Verify that CAPA worked, monitor to ensure problem doesn't return, and close the deviation formally. All steps must be documented. Finding the root cause is the most critical step. Root cause is not the obvious symptom. It's the underlying reason why the problem occurred. For example, problem is machine stopped during production. Symptom is power failure. Root cause is maintenance schedule not followed which led to circuit breaker not replaced which caused overload which resulted in power failure. If you only fix the power, the problem will happen again. Root cause analysis ensures permanent solutions. Root cause analysis tools include the 5 Whys method. Ask why 5 times or until you reach the root. It's simple, effective, and widely used. Fishbone diagram, also called the Ishikawa, categorizes causes into people, process, equipment, materials, environment, and measurement. It's a visual, structured approach. Fault tree analysis uses logic diagrams to map possible failure paths and is good for complex systems. Is and is not analysis compares what the problem is versus what it is not and helps narrow down causes. These tools structure your thinking and prevent jumping to conclusions. Let me give you a cake example using 5 Whys. Problem is cake has mold. Why? Humidity was too high during storage. Why? Humidity control failed. Why? Sensor gave incorrect readings. Why? Sensor was not calibrated. Why? Calibration reminders were not set up. Root cause is no automated reminder system for calibration. CAPA is implement automated calibration scheduling system. This prevents not just this deviation, but future calibration-related problems. For a fishbone diagram example, the problem is late batch release. Under people, analyst was not trained on new procedure. Under process, approval workflow was unclear. Under equipment, HPLC had repeated breakdowns. Under materials, reference standards arrived late. Under environment, lab was understaffed. Under measurement, review process took too long. By mapping all possible causes, you see the full picture. Root cause might involve multiple factors. Common root cause mistakes include stopping too early. For example, saying the operator made an error is not the root cause. Ask why did the operator make an error? Was it per training? Unclear SOP? Rush timeline? Another mistake is blaming people. Root cause should address the system, not the person. If one person can make a mistake, the system allowed it. Treating symptoms is another mistake. Saying we retrain the operator fixes the immediate issue but not the system. Ask why was training inadequate in the first place. Vague root causes are also a problem. Human error is not a root cause. Lack of attention is not a root cause. Be specific, for example, SOP did not include critical warning about X. Every deviation must have documentation. The deviation report includes description of what happened, when and where it occurred, who detected it, and immediate actions taken. The investigation report includes timeline of events, data collected, people interviewed, and analysis performed. The root cause analysis includes tools used like 5 Whys or Fishbone, identified root causes, and justification for conclusion. The CAPA plan includes corrective action, preventive action, responsible person, and target completion date. The effectiveness check includes verification that CAPA worked, follow-up monitoring results, and closure approval. If it's not documented, it didn't happen. Deviations should be managed within defined timelines. Immediate, same day, includes detection and reporting, initial assessment, and containment actions. Short term, 3 to 7 days, includes initial investigation, classification, and root cause analysis start. Medium term, 30 to 60 days, includes CAPA implementation and monitoring start. Long term, 90 to 180 days, includes effectiveness check and deviation closure. Timelines depend on deviation severity. Critical deviations move faster. CAPA is only good if it works. After implementing CAPA, you must verify several things. Did the problem stop? Monitor the same process, look for recurrence, and check related processes. Is the solution sustainable? Can it be maintained long term? Is it practical? Are people following it? Did new problems arise? Sometimes solutions create new issues, so monitor for unintended consequences. If CAPA is not effective, reopen the deviation and investigate again. One of the biggest challenges is that people are afraid to report deviations. Why? Fear of blame, fear of punishment, pressure to meet deadlines, and belief that small deviations don't matter. This is dangerous. Hidden deviations become big problems. A strong quality culture encourages deviation reporting with a no-blame approach that focuses on system, not person, recognition for reporting, transparent communication, and management support. If people feel safe reporting deviations, the system improves. Track deviation metrics including total number of deviations per month, deviations by type such as process, equipment, or documentation, deviations by department, repeat deviations meaning same issue recurring, average time to close deviations, and CAPA effectiveness rate. Trends reveal systemic problems. For example, if 60% of deviations are from one department, investigate why. If average closure time is 120 days, process needs improvement. Metrics drive continuous improvement. Let me give you the key takeaways. All deviations must be documented and investigated. OOT is a warning sign. Act before it becomes OOS. Root cause analysis finds the true problem, not just the symptom. CAPA must be effective, verify it works. Don't blame people, fix the system. Quality culture determines whether deviations are reported or hidden. Deviation trends reveal systemic issues. Documentation is not optional, it's critical. Timelines matter, don't let deviations drag on. In this lecture, we learned what deviations are and why they matter, how to classify deviations by severity, the difference between OOS and OOT, the deviation management process from detection to investigation to CAPA to closure. Root cause analysis tools including 5 Whys, Fishbone, and Fault Tree, common mistakes in root cause analysis, the importance of documentation and timelines, how to build a culture that supports deviation reporting, and the value of tracking deviation metrics. In the next lecture, we will focus on CAPA system, corrective and preventive action. Stay tuned for Lecture 6.